Okay, I think it's time to start again. So sorry that we were a little bit late, and that we will have a break right after this instead. So now I would like to. So we've learned a lot of things over these 2 weeks, and I think that now it's mature enough that you know enough about your system and everything so that we can try and have a workflow of what you're going to do when you go back to your microscope, and hopefully you find this useful. So there's first a workflow for punctofocals, and then afterwards there is a workflow for camera-based systems. And these workflows are not set in stone at all. It's more for you to not forget something, and you can and like a guideline, and then afterwards you can adapt it to your own system. All right, so how to set the parameters on a single point confocal to start with? So we always start with the scientific question. So we have to define for the image that you're going to acquire now. So for each image, let's say, you must have a goal. You don't just go randomly. So if you are going to acquire an overview, your goal is just to see to find the areas of interest. You understand that if you want to acquire an overview and you just want to see that, and you don't care at all about resolution, and you don't want to bleach your sample, so you have this type of constraints in your experiments, and your imaging is going to be completely different from the next image where you are actually at the region of interest and you want to acquire data. So for each image that you acquire, you need to have some sort of a goal. Okay, what are you going to do with this particular image? And in general, it is quite difficult to answer several scientific questions with one image. So very often we need to acquire differently depending on what we want to the goal that we have. So again, what metrics do we want to measure in this image? And if we acquire an overview, what we want is the XY position of the areas of interest. There's no image analysis, or maybe there is. And then all we want is a list of positions where the areas of interest are. And how big are the differences from if you have like two different samples, treated or not treated, and all this influences the way you're going to how fine differences you want to see between the different images. So from that, we're going to deduct the resolution that is required. In an overview, we need very low resolution. So we're going to have everything minimal as possible. So once we know the required image resolution, we're going to decide which objective we want. For example, for an overview, we want a large field of view, so we're going to go to the smallest magnification possible. So you choose the objective that delivers the optical resolution that you want, and then you check that the other parameters like working distance, the field of view, the immersion medium, work also with your constraints of your experiment. And one thing that I want to mention is that I have seen that several people feel a bit overwhelmed. It's a lot of information and everything in the course, and clearly there is. But I want to tell you that as we go through this workflow, I want you to realize that everything we are going to talk about all these things are things that many of you were absolutely not aware of, and many of you now are very comfortable with. So yes, it's true that there's a lot of information and you do not know all the details, but you will see that you have actually learned a lot during these 2 weeks, and you feel comfortable with concepts that you didn't know anything about before. So that is actually a big achievement. So working distance, field of view, immersion medium, hopefully you are very comfortable with these concepts now. So then we have to do our homework with the fluorophores. We make sure that our fluorophore combination matches the microscope excitation and emission specifications, and that we do not have any bleed-through, okay? That we image efficiently and that we do not have bleed-through. So I hope everybody's comfortable also with these concepts. And then we're going to have an imaging strategy. Do we image sequentially or simultaneously? Do we combine channel? Do we image spectrally? And again, if you have a camera-based system, it is very likely that you have no such option, and all you need to do is image sequentially. But if you are working on a single point confocal, you may be able to combine the channels or image spectrally or image some simultaneously. So this is something you have to decide based on this. And then you want to anyway avoid bleed through while optimizing the acquisition time. So this is your image strategy when you go with your sample to the macroscope. This is when you need to decide this if you're working with a single point confocal. After that, you're going to change the display. So you're going to make sure that the images are in black and white so that you avoid the color bias, and you push the lookup tables to increase the brightness and contrast so that you see the dim areas as well. And then you're going to check the pixel intensity in and out of the region of interest, so you can estimate the signal to background ratio in your sample by just hovering your mouse in the pixel of interest, and then outside, then you can see the signal to background ratio. And always use the saturation and underexposure lookup tables, regardless of the type of sample that you have, so you don't get tricked and believe your eyes. So now we're on the single point confocal. The next thing, now we have designed our experiment basically, and we have decided how we're going to image. And what we will do now is that we are going to set the scan area. So what we want with the scan area is that we want the area of interest to fill the image. We do not want to have, as Marie was showing, one little cell with like tons of black around. This is a waste of everything. A waste of resources. So what we want to do is adjust the scan area and zoom in until the object of interest actually almost fills the field of view. So very little black around. Right. So yes, here we go. Once we have the scan area, we need to decide how many pixels we're going to put in it. So that is going to determine the pixel density, and it will determine the image pixel size, right? So what we do is that we ask ourselves, what is the pixel size that fulfills the Nyquist criterion for these conditions? So this objective, the wavelength, and the scan area. What is the pixel size? Well, all you need to do is click on the optimal button, the magic button, and then you will find out. So the software automatically sets the image pixel size to about half of the optical resolutions, and as you have seen, there are different calculations. It's okay, it's about there. And then the next thing you push that button, the pixel size becomes the Nyquist pixel size, and then you can ask yourself, do you need to use such small pixels to answer your scientific question? Yes, if you want to resolve all these, everything that is resolved by the objective, you must have it. Otherwise, you do not resolve everything that in a digital image, you do not resolve everything that is resolved by the objective. So yes, if you need that resolution, you absolutely must keep these small pixels. Then you can ask yourself, can you afford to use such small pixels? And that is a problem if you have some issues with bleaching, with light toxicity, for example, in live samples, live sample, then you may not be able to actually use such small pixels. Maybe you will have to compromise and use bigger pixels on the sample, create some artifacts, but get away with less light toxicity. So we always have to compromise. But basically, these are the questions that you're asking yourself. And if you decide to undersample, you should acquire a few images at Nyquist sampling and undersample the way you would like to image, and you compare them, you analyze them to understand the impact of the aliasing artifacts and the lower resolution on your interpretation of the images. So you do this little test, it takes seconds really, it's acquiring a few images undersampled and a few images at Nyquist sampling, and you compare them, and then you are able to make an educated decision about what is the pixel size that you're going to have in your image. Okay, do you go for the Nyquist pixel size or will you undersample? and how much. So this is scan area, how many pixels do we put in there? And then we go to the pinhole. So the pinhole size, what do we do there? So basically, when we are imaging several fluorophores at the same time, we have only one pinhole, but we have different wavelengths. So you know that the pinhole size is related to the size of the point spread function, the main lobe of the point spread function. And this point spread function is related to the wavelength. So it means that hopefully we should have different pinhole size for different wavelengths. However, we have only one pinhole. So now we have to make a decision. Let's say if we have blue, we image blue, green, and red and far red a sample with 4 colors. What is the pinhole size that we're going to use? So I remind you, this is the point spread function. This is 1 area unit, and this is what happens when we set the pinhole to 1 area unit. And so this is the physical size of the pinhole, is the diameter of the point spread function. So this is the radius, so it doubled the optical resolution, and it's magnified, so it's multiplied by the magnification of the objective. So that is the physical size of the pinhole. So what are we going to choose? Which wavelengths are we going to choose for that? You need to ask yourself about the design of your experiment and your scientific question. If you, for example, let's say that you have DAPI in the blue, and then your important protein is in the far red. What happens if you set the pinhole for the shorter wavelengths? The pinhole will be too small for the longer wavelengths, okay? So you're going to lose a lot of light in the longer wavelengths if you set your pinhole at 1 area unit for the DAPI. Now you need to ask yourself, do you really want to have the best resolution in DAPI? Is this important? Or if your far red signal is dim, maybe it's more important that you get more light there. And in that case, you would set the pinhole for the longest wavelength, okay? So, and then this is what would happen when you go to the longer wavelengths. Otherwise, you're going to crop your point spread function and lose some light. If, on the other side, you want to have the best contrast on the longer wavelength, maybe you are going to set the pinhole for the longer wavelength, and then what will happen is that the blue image will have lower contrast because the pinhole will be too small for the blue light. Okay, so this is fine adjustment of the point spread function of the pinhole size, and different manufacturers will have a different strategy when it comes to the pinhole size. In Zeiss, when you press the 1 area unit button, they will automatically set the pinhole to the shortest wavelength, which means that everything else will have their point spread function crop and will be dimmer. Okay? In the Nikon system, when you press the 1 area unit button, it's the opposite. They choose the pinhole size for the longest wavelength, which means that you're not going to be at 1 area unit for the shortest wavelengths. Very often in the blue, we have DAPI, for example, and there we do not need the best resolution, and it's very bright. So I think that having the pinhole set for longer wavelengths is actually quite a good option. But this is something that you need to decide yourself. Where do you want to have the pinhole at 1 area unit? So that's about the pinhole size. And if you have very dim sample and no high XY resolution and contrast is required, you can also open the pinhole more than 1 area unit. That's also totally okay to get more light. And then if you have a very bright sample and you can benefit from closing the pinhole smaller than 1 area unit, and then you actually increase the XY and the Z resolution. So the pinhole size is, you have several choices that you can make here, and so you can choose knowingly. Next, we're going to set the laser power. So what are our choices there with the laser power? If bleaching and light toxicity are a problem, clearly you want to stay low with the laser power. So if you have live samples, or you're doing a Z-stack, or you have dim samples, maybe you want to be very careful with this. Z-stack, I remind you that we're bleaching also above and below the focal plane. So that's why we have to be careful with bleaching when we do a Z-stack. we have 20Z, we're going to bleach the whole volume 20 times. So otherwise, you can increase the illumination laser by no means stay at 1% all the time, please. So if you increase the illumination laser, if you the illumination light, if you can afford, then you're going to reduce the short noise contribution. So your signal to noise ratio will be better, and the image analysis will thank you for that. So this is the compromise. So if you can increase the illumination power, just do it. After setting the illumination, we're also going to change the detector gain and the offset. More modern confocals, in more modern confocals, the offset is set automatically. It's calculated in a different way, so you don't have to bother with this. But if you have an offset, you have to choose what level you have. So to set the gain, you want to have a high signal. I remind you that the gain amplifies the signal. We want to have a high signal, but we do not want to create noise. And a very high gain produces noise. So never push the gain super high to its like top 30%, okay? You prefer instead to stay with a slightly lower gain, like it depends on the type of detector, if you're going to be more towards half or more towards the first third of the slider. But basically, you don't want to go too high, and just keep an eye on the noise when you're increasing the gain. And so it's at some point when you start seeing that your images get noisy, instead, you can lower the gain again and then slow down the scan and increase the laser power to compensate. So in all these things, anyway, you do not want to have any saturation in all the areas of interest, and you do all this with the lookup tables to see saturation and not the exposure. When it comes to the offset, so this is the lower level of detection, so the dim pixels. How much of the dim light do we get? Basically, what you need to do is that you turn off the lasers and you acquire continuously, so you have a live image, and you have the underexposure saturation and underexposure mask on, and then you lower slowly the detector offset one by one until you have no intensity, no blue pixels in the background. So no pixels with an intensity at 0 in the image, okay? And this is your good level of offset, then you can turn back on the laser. So this is for the gain and the offset. And then you're going to check the noise in the image. And again, the noise comes mostly from shot noise, which is the fact that we image with light. And the best weapon we have against shot noise is increase the amount of photons that the detectors get. So you acquire a 3-image time lapse. We've done that without interval, and then you play it to estimate the noise, and you ask yourself if the noise prevents you from answering your scientific question. And if it does, then you need to improve the signal to noise ratio, for example, by increasing the illumination intensity, or you can also average. Then we're going to choose the pixel dwell time as well. And so the pixel dwell time is the scan speed. By default, you should go fast. So you try to stick to the fast scan speed. That is because you want to avoid sending the fluorophores to a dark state. And when you shine a lot of light for a long time, you increase this probability. Then you will get apparent bleaching. So you try to go for fast scan speed, and you only slow down the scan speed if you have no more option to reduce the signal to noise ratio, to improve the signal to noise ratio. So if all other noise reducing strategies are insufficient, then you go down to a lower scan speed. Okay. So you have a higher pixel dwell time, the time it stays on each pixel. So now I want to show you, so now that's it for the point confocal. You see, it's not so many things, and we have gone through all these steps one way or another. So I hope that you will find this little guide useful when you are sitting by the microscope to make sure you are not forgetting anything. Then afterwards, you can change the order and decide for yourself, but you have at least a little guide. So here is what I want to show you. I hope that you can see all the little dots in the image. But basically, this is a low detector gain and this is a high detector gain. And now I have no light. So this is not fluorescence, this is noise. There's no laser. I'm just imaging with no excitation light. And basically, you can see the impact of increasing the gain of the detector on the noise. So high detector gain means a lot of noise in the image. So try to avoid that. So I want to say a little something about the automatic settings because these are very popular with the vendors. It's very easy for them. They say push that button. Oh, great, that's it. So clearly, it's very user friendly, which is nice. And I think it's a very good way to start when you are at the microscope and you want to get started. You can push that; it goes fast, but you need to check what the software does because the software doesn't know what your experiment is. And you have in general one or two options to say I want to go fast or I want to get the best resolution or something like this. So the automatic settings are great, but you always need to check what the software has done and if that matches your scientific questions. You should have no bleed through between the co-excited channels. So co-excited means you are exciting them at the same time. So there should be absolutely no bleed through. And again, the software doesn't know how bright your sample is. If you have one channel that is much brighter than the other one, the software is anyway going to tell you the same solution as if all of them are at the same level. But in one case, you're going to see some bleed through, and in the other case, not. So that's why you need to check. And if you have, I remind you that even if you image sequentially, if you have cross excitation and bleed through, you're in trouble. Okay, so it's not because you're imaging sequentially that you have to just forget about bleed through. That is not the case. If you have cross excitation and bleed through, even sequentially, you will get to see the bleed through in the wrong image. So make sure you have no saturation and no underexposure. Again, it's the same thing. When you press the button to set everything automatically, the software doesn't know that in a different Z stack, you're going to have some saturation, for example. All these type of things you have to do yourself. So the automatic settings also do not set the zoom or the pixel size because they have no information about your sample. So you have to do this yourself. And you can do that following the little guide I had before. For the same reason, the laser power, the pixel dwell time, and the averaging might be incorrect because the software has no information about your sample. So please check, use these automatic settings, but also check what the software is doing. And now we can look at what happens on a camera-based system. So before we start on a camera-based system, I would like to ask you guys if you have any questions about the part on single point confocal or comments. Everything is does it make sense for you what we are doing in each of these steps?
So I will need to try just to see it in the confocal and do it, but yeah, for me it was clear.
So it's very good. You need to try. So when you go back to your microscope this weekend, you can follow this little guide and see if this helps you set all the parameters correctly. At least you have some sort of a summary that tells you which parameter does what, as a little reminder.
Yes, that's very good. Thank you.
Okay, so I continue on the camera-based systems. So we always start with the scientific questions, exactly the same thing. What are you going to do with this particular image? You do not set things in the same way if you want to acquire an overview or if you want to measure the size of mitochondria. So then from there, you are going to decide which objective will deliver the optical resolution that you need, and also the working distance, field of view, etc. That is driven by the scientific question. Then you check your fluorophores, they must be imaged efficiently, and you should avoid bleed through. On a camera-based system in general, we image sequentially, but for some reason, people who work on single point confocals, they think that if they image sequentially, they are totally safe. Whereas people who work on camera-based systems, they always image sequentially. They are very aware in general that they can get bleed through. Okay, so you guys who work with single point confocals, stop thinking that you are safe if you image sequentially. It is not true. If you have cross excitation, we are in the same situation as everybody else. So then we check the display, so it's the same thing, black and white, this saturation mask, etc. And then we want to estimate the signal to background ratio. We can also estimate the signal to noise ratio. And then we can decide, for example, in some cases, oh, I want to go very fast. I want to have a brighter signal, so I'm going to use some binning, and I will compromise and have a lower digital resolution. So it's a compromise. So you can decide, are you going to have binning or not? By default, you should not use any binning. And then when you need it, then you add the binning. And then when the full resolution of the camera is not needed. And also if you want to go faster and image brighter images and have smaller files, you will use binning. Then we are going to figure out if we have a magnification lens. And so not everybody has an extra magnification lens, but this weekend I think we will have to figure out and let me know. So hopefully a few of you will discover that they have that and that they can use it. And if not, you may be able to convince your boss that it's needed so that you could use some of the objectives with at Nyquist sampling with a bigger field of view, for example. And then we're going to consider the camera pixel size, and then we calculate the objective. If the objective magnification is sufficient for this camera pixel size to fulfill the Nyquist criterion, and that means that we would have the image pixel size would be half of the optical resolution. And if not, maybe we want to add the extra magnification lens to avoid artifacts. So, and then we're going to choose the camera area. So this is one of the things that Marie showed a little bit at the end. If we have a sample that does not fill the whole field of view, we have the possibility to crop and only use some pixels at the center. So it just means that we turn off the pixels on the outside of the chip. But otherwise, it's not like in a point confocal where we zoom in and out. There's no zoom. We just turn off some pixels. But it allows you to go faster and has several advantages. And one of them is that you end up with an image where the area of interest fills the image without unnecessary information around. So please use the camera crop function. And I think one of the things you have to show me is where it is in your software, people with a camera. So you will have to use it this weekend. Then we're going to choose the readout noise. So I think everybody pretty much has a readout noise. Sometimes it's not called that way. Sometimes the manufacturers call it like like very fancy names like speed or sensitivity or something like this. But basically, this is what it is. It's a readout noise. And if you, by default, you should use a low readout noise. So it's in megahertz. So you should use a low readout noise to avoid creating noise. But if you want to image fast, for example, you image calcium imaging or something like this, then you will have to increase the readout rate and compromise with the signal to noise ratio. Then we choose the illumination power. It's the same thing. If you can afford to increase the illumination power, do it, because you will improve your signal to noise ratio. Some cameras have a gain and an EM gain. It depends on the type of camera. If you have these options, you can test different settings and choose based on the signal to noise ratio that they give. Then you can decide to average or not. The way you do it is that you scan continuously. You ask yourself if if you can answer if the noise prevents you from answering your scientific question. And if it does, then you add some averaging and then you test again. This is the way to to check if you need averaging. And then we would need some background correction. I remind you that the camera manufacturers always have an offset. And if you want to extract whenever you want to extract some intensity information from an image acquired with a camera, you should remove the offset by doing a background correction. And depending on how you do it, you may also remove the autofluorescence, for example, in your mounting medium. Okay. So you acquire an image with a short exposure time to know the camera offset, no illumination, short exposure time, click one image, and then you look at the average of the intensity value in the whole image, and that tells you if the camera offset that is set by the manufacturer is 100 or anything else. Another thing with a camera-based system, especially actually pretty much only on the wide field systems, sometimes the illumination is not perfect. And in that case, you would use a shading correction algorithm to correct for that. So this is what I wanted to do, what I wanted to say for this little workflow. And I'm just looking now at my timing. Yeah, not bad. So I wonder if you have also any questions for this part on the camera-based part or comments.